Let's do another optimization problem. Each one brings its own little tricks and quirks and geometries, so at first you just got to kind of do a few and try to catch on to the patterns as we go. So find the dimensions of a 4-liter cylindrical can that uses the least metal to make. Take a second. Can you figure out what this is asking? Can you turn this into a math problem? Can you model it? If not, let's go ahead and break this down a little bit more. So they're asking for a cylinder. Let's go ahead and draw a cylinder. Here's my quick cylinder. Doesn't have to be too pretty. In fact, that's really not pretty. Let's clean that up a little bit. A little better. Okay. And we want to know how much metal it takes to make. So the thing we are optimizing here is the amount of metal. But really, that's going to be surface area. Okay. So it would be nice if we had a formula for surface area. I think we can probably figure this out. If you're not so familiar, let's walk you through the surface area of a cylinder. So it comes in two parts. The part that always throws people off is just the outside, right? If this was a soda can, the wrapper. That's exactly how you should think about this. This is this surface area for this outside here is like a wrapper. It's a rectangle. It's just wrapped up into a circle. And so we need two things to find the area of a rectangle. We're going to need how tall it is. So let's go ahead and label that over here, h. Okay. And we also are going to need to know how wide it is. And in that case, how wide it is actually the circumference of this circle. So let's go ahead and label that radius there. And then the circumference of a circle is the diameter times pi. So in other words, this is 2 pi r. That's the circumference times the height. Let me go ahead and draw that out a little bit over here. So if we took the wrapper on that can and we unraveled it, we'd have a height like that, and then the distance around is really the circumference of a circle, so that is 2 pi r. Okay, you do need to know the circumference of a circle. It's where pi comes from. So if you have a circle, the definition of pi is it is this magic thing such that pi times the diameter equals the circumference. That's how we define the number pi. What's magic about it is that no matter where or what size a circle is, it's always the same number. Okay, so it's always pi. From there, you just need to know that the radius, that 2 radii make up 1 diameter. Okay, so that is just the one circle on top. Sorry, not one circle on top. That's just one time around. That's that wrapper. We still have the circle on top and the circle on bottom to tack on to the surface area. I think I know the area of a circle. So that's pi r squared, but I've got 2 of those. Okay. So that should be it. So surface area we can usually just break down into the different sides involved. So I want to find a minimum of that for the least amount of metal. Notice how there's an r and an h. We've got those 2 independent variables, which is leading us to immediately think, hey, can I get rid of one? And that is where our constraint comes in, our restriction comes in. Okay. And the constraint here is that 4 liters. What is 4 liters? That's going to be my volume. Okay. Do you know the volume of a cylinder? Okay, we've talked about this before. A cylinder is really a type of prism. It's just taking the area of that circle and then multiplying it out by h. It's extending it out. So it's just going to be V is equal to pi r squared, the area of the base, times h. If the base wasn't a circle, if it was a triangle or a rectangle, then that pi r squared would just get replaced by whatever the area of that base is. Okay, but in this case, we know that that is actually 4. We want to take that constraint and we want to solve for one of our variables. So let's go ahead and write that 4. It's up to you which one. Sometimes one is easier than the other. It might be a little easier here to write h is equal to 4 over pi r squared. Okay, I think that's actually probably the easier choice. Sometimes one doesn't end up being easier than the other. One of the reasons is because there's no square roots if I do it this way. The other is that h only shows up once over here. So I'm only going to be replacing one of them. So let's go ahead and substitute in. I say plug in, but really this is a substitution. S is equal to 2 pi r, my new formula for h, 4 over pi r squared, plus 2 pi r squared. Cool, amazing. So what we've done by our constraint is two things. We've gotten rid of that h, which is great, but also if you don't incorporate the constraint, then there's nothing stopping you from making a cylinder with no height or no radius, right? You could just make a non-existent cylinder which would use no metal, or even negative cylinder which would use negative metal. I don't even know what that means. Often after plugging in, it is worth taking a second to try to simplify this thing, make your life easier. So it looks like that r squared and that r are going to cancel, and the pi's are going to cancel. So in particular, this pi goes with this pi, the squared goes with this r, and then I'm going to get an 8 out. So I get 8, oops, wrong color, 8 over r. I'm going to write this r to the negative 1, help my derivative in a second here, plus 2 pi r squared. Okay, so once I get that, now it is time to find that minimum. All that work was just modeling, and then using that model to kind of get the simplest expression possible. Now this is a calculus problem. So no one part of math operates on its own. Okay, we got to really think through this to get to the calculus part. Finding a minimum, and yes, it's up to you to realize you want to find a minimum here. Well, now this is a matter of taking a derivative and setting it equal to 0. So I'm going to take s prime, or in this case, I do like to be specific. Lots of people do write s prime, but I'm going to write ds over dr, because it's going to look a little different than if someone did a different substitution and they got ds dh, say. So I like to write ds dr. I know how to do this. This is now negative 8r to the negative 2 plus 4 pi r. Okay, notice also that because this is just a one variable situation, I'm taking the derivative with respect to r, I don't need to play that implicit differentiation game, right? I don't need some secret dr coming out. So in some ways a little easier than related rates. In other ways harder. Okay, I found the derivative. What do I do next? That's right, I set it equal to 0. 0 equals negative 8r to the negative 2 plus 4 pi r. Take a second, make sure you know how to solve this. This might be a little bit of a kick in the head to remember how to solve for r in situations like this. There is more than one way to do it. I'm going to go ahead and give you just a second here. Okay, lots of ways to deal with this. Probably the easiest way right now is just to multiply both sides by r squared. Now I'm allowed to do this. I mean, I'm always allowed to do this, but notice that r is not going to be 0. So that does reassure me that this is a fine thing to do, because my radius of this can't be 0. So let's go ahead and multiply by r squared, and I'm just going to get 0 equals negative 8 plus 4 pi r cubed. Now what do I do? Well, it looks like 8 is equal to 4 pi r cubed, isolating that r. In other words, 2 over pi is equal to r cubed. R is equal to the cube root of 2. Sorry, r is equal to the cube root of 2 over pi. That's a nice number. Okay. Almost there. Still got to plug back in for h. H is equal to 4 over pi times, well, now I got to plug this whole thing in. This looks like 2 over pi to the 2/3. Cube root is that third. I'm squaring it so I get that 2. This does simplify. In fact, maybe I'll just leave it like this. I was gonna go ahead and write out the more simplified version of this, but well, let's go ahead and leave it for now. Okay, those are my dimensions. You might say it doesn't look very pretty, but it's actually not that long compared to other expressions I might write. It didn't actually take that much longer than writing 8.25937. And you could certainly bring in that pi in that h to clean that up quite a bit. Okay, great. So that was the problem. There's one more thing I want to say about this after we just talk about the steps again. We made sure we understood it. We drew a picture, which gave us a model. We found what we're optimizing and what was our constraint. We used that constraint to get rid of one of our variables, and then it was just a calculus problem of taking the derivative, setting it equal to 0. We should actually check that this thing is a minimum, but notice that there really is only one place where this is differentiable, or not differentiable. That's at 0 because of that r to the negative 2. And we know r has to be positive. Really, we can kind of infer without doing a first or second derivative test. We usually can that this must be a minimum, right? As r gets really big, then clearly my surface area is going to get very, very big. Same with as h gets really big. So this is my nice minimum. There is one other problem here, and I usually don't talk about dimensions, but I think we need to talk about units. I think we need to talk about units real quick. This is not a great answer because it's unclear. It's unclear what our units were. We just said volume was 4, but right up here, this is for liters, and it's not really obvious what units for h and r would give me liters. It ends up being decimeters, I believe, as our units for h and r. So probably the better thing to do here, especially for our physics and engineering people, is to change 4 liters into 4,000 cubic centimeters. And then what that does is it means that what you get out in the end is centimeters for all of your units, as opposed to this weird unit of decameters to make it work out. So there is 1,000 cubic centimeters in a liter. Converting these liters into centimeters is going to make your unit analysis much better. And really to work through with 4,000 changes very, very little. It just means that this 4 becomes 1,000 here, right? Which means that everything kind of gets multiplied by 1,000 for all of these as well. Right, all those 8s become 8,000s. So you can redo that with a couple extra zeros if you want to. If I was being a little more careful with units, that's what we should have started with from the beginning. Yeah, take a second at the end and see if your units make sense. All right, a couple more examples in the future, but that is it for this one.